Hey everybody, Apologia Chemistry 3rd edition, week 5, day 4, textbook pages 93 to 104. Isotopes and nuclear bombs. Before we leave this discussion of protons, electrons, neutrons, and isotopes, we should point out one more thing. If you pay attention to the news at all, you have probably heard about how the United States and other nuclear powers in the world are trying to keep nuclear technology away from certain countries and are concerned about those countries that are developing nuclear technology. Have you ever wondered what exactly nuclear technology is? Most people would say that it refers to the ability to make a nuclear bomb. In fact, that's not true at all. Any person who has studied nuclear physics at the college level has all of the knowledge needed to build a nuclear bomb. The trick is not in making the nuclear bomb. Almost anyone with a little training can do that. The real trick to making a nuclear bomb is in making the bomb's fuel. Uranium is the usual fuel used to make nuclear bombs. However, the element uranium has 3 naturally occurring isotopes, U-238, U-235, and U-234. A sample of natural uranium is about 99.3% U-238, about 0.7% U-235, and less than 0.01% of U-234. Only the U-235 isotope can be used to make a bomb. For a nuclear bomb to work, the uranium used in this bomb must have a significantly larger percentage of U-235 than natural uranium has. In other words, to be able to produce a nuclear bomb, the amount of U-235 in the uranium used must be artificially increased. The way to do this, of course, is to get rid of some of the U-238 in the uranium. This process, called isotopic enrichment, is very tricky. After all, the only real difference between U-235 and U-238 is the mass. Chemically, they behave in exactly the same way. This makes it nearly impossible to separate them for isotopic enrichment. Of course, nearly impossible and impossible are 2 different things. During World War II, scientists in a group called the Manhattan Project were able to figure out a way to partially separate U-238 from U-235. The process is incredibly inefficient, but it is able to take natural uranium and enrich the U-235 content from 0.7% to a little more than 7%, which is enough to fuel a nuclear bomb. Ultimately, making a nuclear bomb is simple. However, getting the fuel to power it is nearly impossible, and the technique for making this fuel is difficult and not readily shared. Atomic structure in more detail. This is a longer section. Feel free to just read it on your own if you'd like. It starts at the bottom of page 93, and it continues all the way to page 98. If you'd just like to listen, here you go. Now that you know how to determine the number of protons, neutrons, and electrons in an atom, you might ask how these particles arrange themselves in an atom. Are they jumbled together like a bunch of marbles in a sack? Do they arrange themselves in groups? Do they form any neat arrangements or designs? These are the same questions that chemists were asking themselves in the early 1900s. After electrons were first discovered, and before neutrons were discovered, chemists thought that an atom looked a lot like a dish of plum pudding. This concept, called the plum pudding model, was developed by British physicist J.J. Thomson. Here you see, this is the plum pudding model that we're talking about. In essence, chemists thought that the atom was made up of a pudding-like substance which had positive electrical charge. Electrons, they thought, were suspended in this pudding, like plums, making the entire atom electrically neutral. Remember, it's impossible to see atoms, so chemists just had to imagine what an atom might look like. That's why we call this concept a model of the atom. A model is simply a constructed image of something we cannot see with our eyes. Since we can't see atoms, how do we know whether or not the plum pudding model is correct? The best way to determine that is to compare it to experimental data. If the model is inconsistent with the experimental data, then the model is obviously incorrect. However, if the model is consistent with the data, then we don't necessarily know that the model is right, but we at least know that it might not be wrong. The trick is in designing an experiment that will produce data that really test all aspects of the model. Ernest Rutherford, who was Thomson's student, designed the perfect experiment to test the validity of the plum pudding model. In earlier experiments, Rutherford had identified a type of radiation called alpha particles. He determined that these alpha particles have positive electrical charges and are emitted by certain isotopes that we call radioactive. You will learn a great deal more about radioactive isotopes if you take advanced chemistry. For now, just remember that alpha particles are positive particles emitted by certain radioactive isotopes. Rutherford decided that what he needed to do was to shoot some of the alpha particles at a thin metal foil. He reasoned that if the plum pudding model of the atom were correct, the alpha particles should pass through the foil without changing the direction much. After all, the positive alpha particles would be attracted by the negative plums, or the electrons, but repelled by the positive pudding. Since the plums were randomly distributed around the pudding, the alpha particles would be attracted and repelled in many different directions, and the result would be that they would travel straight through the atom. If you have trouble understanding why the alpha particles should travel straight through a plum pudding atom, think about it this way. Suppose you were trying to move a large boulder by tying many ropes to it and having several people pull on the ropes while others pushed on the boulder. If everyone pulled and pushed in different random directions, the boulder wouldn't go anywhere. To move the boulder, everyone would need to pull in one direction and push in roughly the same direction. The same principle applied here. When traveling through a plum pudding atom, the alpha particles would be pulled and pushed in different random directions. This would result in the alpha particles not being moved from their original path. We hope that you can see the ingenuity behind Rutherford's experiment. The data provided would be an excellent test of the model in question. If the alpha particles did not behave as Rutherford expected, then clearly the plum pudding model was wrong. However, if they did behave as expected, then that would be one more bit of evidence in favor of the plum pudding model. In this experiment, Rutherford put a radioactive isotope in a thick lead box with a single hole in it. The radioactive isotope inside the box was emitting alpha particles, which was a type of nuclear radiation. Most of the alpha particles were stopped inside the box, but any that were emitted in the direction of the hole escaped. This made a beam of alpha particles that could be pointed toward a target. The beam was narrowed by another piece of lead with a hole in it. In the end, Rutherford built an alpha particle shotgun out of the lead box that directed a thin beam of alpha particles to hit a thin piece of gold foil. Rutherford surrounded the target with a zinc sulfide screen. When an alpha particle hits zinc sulfide, a bright green glow is emitted. Rutherford could see where the alpha particles went after they collided with the gold foil by simply looking at where the zinc sulfide screen was glowing. Wherever it was glowing very brightly, many alpha particles were hitting it. Wherever it was glowing faintly, only a few alpha particles were hitting it. Rutherford ran his experiment, and to his astonishment, the zinc sulfide screen glowed everywhere. The glow was the brightest directly in front of the target, but alpha particles were hitting the zinc sulfide screen at all other positions as well. Rutherford noticed that the farther away from the front of the target, the dimmer the glow was. Nevertheless, alpha particles were colliding with the target and bouncing in every conceivable direction. This, of course, spelled the end of the plum pudding model of the atom. After all, there was no way to imagine how the alpha particles could possibly bounce off of the target and change direction if the plum pudding model of the atom were correct. Rutherford tried his experiment with several different types of targets to make sure that his conclusion applied to all atoms. In the end, the results were the same, regardless of what target was used. Of course, it wasn't enough for Rutherford to simply determine that the plum pudding model of the atom was wrong. Now that he had all his experimental data, he needed to try to develop a new model of the atom that was consistent with all the information he had up to that point. Rutherford developed such a model and called it a planetary model of the atom, but it is usually referred to today as the Rutherford model of the atom. This one right here, the Rutherford model. In Rutherford's model, the protons were clustered together at the center of the atom, called the nucleus, while the electrons orbited around the nucleus in the same way that the planets in our solar system orbit around the sun. This similarity between his view of the atom and our solar system is why Rutherford called it the planetary model of the atom. Notice that Rutherford's model does not contain neutrons because neutrons had not been discovered yet. Realize that this idea of what the atom looks like was not something Rutherford just dreamed up. It was the only feasible model that explained the data he got from his experiment. Remember, Rutherford's experiment showed that when positive particles were shot at atoms, most of those particles passed through the atoms undisturbed. However, some were deflected away from their original path. Sometimes the deflection was enormous and the alpha particle would bounce backward after hitting an atom. Rutherford's model is consistent with all of this data. In this figure, the arrows represent alpha particles that are passing through the atom. Unlike the plum pudding model, this model has a positive electrical charge concentrated at the center of the atom. The negative charges, which are the electrons, are orbiting around the protons. Since the electrons are not concentrated in one spot, they do not affect the path of the alpha particles greatly. The protons cause most of the deflection of the alpha particles. The vast majority of alpha particles that pass through the atom then will not be deflected because they will pass through the atom far from the protons. These alpha particles, represented by the straight arrows, will continue to travel straight, hitting the zinc sulfide screen in front of the target. However, if an alpha particle passes through the atom close to the protons, it will be repelled by the proton's positive charge and will be deflected from its original path. The closer it passes to the protons, the more its path will bend. If it is headed directly toward the proton, it will be repelled so much that it will turn around and head in the opposite direction or appear to bounce back. These deflected alpha particles are represented by the curved arrows. The vast majority of alpha particles are not deflected because they do not pass very close to the protons and they strike the zinc sulfide screen directly in front of the target, as Rutherford saw in his experiment. Rutherford's observation that the number of alpha particles that were deflected is very small It also makes sense in terms of this model because the number of particles that pass close to the protons is quite small. In the end, then, Rutherford's model was consistent with all of the data produced in his experiment. The one thing Rutherford's model was not consistent with, however, was a current theory in physics. Physicists during Rutherford's time had noticed that whenever electrically charged particles moved in circles, they emitted light. When they emitted this light, they would lose energy and slow down. According to this theory, the Rutherford model of the atom would never be stable. This theory would predict that the electrons moving in a circle would continue to emit light until they lost all of their energy. It would also predict that as the electrons lost energy, they would spiral toward the protons in an atom until they collided with them. Even though Rutherford's model was not consistent with the current theory in physics, it was the only model of the atom that could be devised that was consistent with his experimental data. It became the accepted model of the atom until it was later modified by Niels Bohr. To understand Bohr's model of the atom and what experiments led up to it, you must first learn a little bit about light. So here's the Bohr model right here. The nature of light. In Model 1, you learn that since light neither has mass nor takes up space, it is not matter. However, you haven't yet learned what light is and what its properties are. That's the purpose of this discussion. The first thing you must realize about the nature of light is that scientists don't completely understand it. There are currently two models of light, the particle model and the wave model. The particle model states that light is made up of small particles called photons. Any beam of light that you see is made up of billions of individual particles, photons, that are all traveling in the same direction. The wave model, on the other hand, says that a beam of light is a wave that travels much like the wave on an ocean. To make things even more confusing, sometimes light behaves like a particle, and sometimes it behaves like a wave. Scientists really aren't sure they understand this phenomenon, but they accept it. Currently, theory states that light acts like both a particle and a wave. The situation that light is in determines whether it will behave as a particle or a wave. Scientists call this theory the particle-wave duality theory, and it is used frequently in describing light. Particle-wave duality theory is the theory that light sometimes behaves as a particle and sometimes behaves like a wave. If you don't understand the particle-wave duality theory, don't worry. Scientists don't understand how light can be both a particle and a wave. But for now, we are forced to believe it because that's what the experimental data indicates. The wave model of light is by far the most useful way to picture light, so let's start there. Down here. This is one way to picture light. It moves through space just like a wave moves through water. The high points on the wave are called the crests. So we have a crest here and here. And the low points are called troughs, down here and here. If we were to describe the above wave, we would need to specify two things. First, we have to say how far apart the waves are. We use the term wavelength to accomplish this. The wavelength is defined as the distance between the crests or the troughs of a wave. Since wavelength is a measurement of distance, its units will be meters, centimeters, etc. The wavelength of a wave is usually given the symbol lambda, which is the lowercase Greek letter lambda, as illustrated in the figure right here. To describe the wave completely, we not only have to tell how far apart the waves are, we also need to tell you how big the waves are. This is referred to as the amplitude of the wave, and that is defined as a measure of the height of the crests or the depths of the troughs of the wave. So the amplitude is going to be how high the crests are or how deep the trough goes. Amplitude is usually given the symbol A, as illustrated. Amplitude is not a distance measurement, however. The units for amplitude vary from wave to wave, and we will not get into those distinctions here. If you take physics, you will learn about the units of amplitude. For now, just remember that amplitude means how big the wave is. The larger the amplitude, the bigger the wave. How does all of this apply to light? The wavelength of light corresponds to its color. Perhaps you have seen what happens when sunlight hits a prism. Once it passes through the prism, the apparently white light turns into a rainbow of colors. This is because, through laws that you will learn in physics, a prism breaks light into its different wavelengths. Each color you see represents a range of wavelengths. Think about the last time you saw a rainbow. What colors did you see? Red was at the top of the rainbow, orange was next, yellow followed orange, and then there were green, blue, indigo, and violet. These are the basic colors of light, and they always appear in a rainbow in that exact order. Why? For example, red light is made up of waves whose wavelengths are between 650 and 700 nanometers long. The prefix nano means 10 to the negative ninth. So red light's wavelengths are very, very small. However, of all the colors, red has the longest wavelength. This range of light wavelengths is typically called the visible light spectrum. You will learn why it is called this in a little bit. As you will learn in physics, the wavelength of light determines how the light passes through a prism. Since wavelength determines color, the colors of light in a rainbow always appear in the same place because they always pass through the water droplets in the air in exactly the same way. Although you needn't memorize the wavelengths that each color corresponds to, you do need to memorize the relative size of the wavelengths in question. That is, you need to know that red light has the largest wavelengths, orange light has a smaller wavelength, and so on. This is easy if you think about the colors as a single name. The first letter of each color is listed in the figure in boldface type to emphasize that when you put them together in the proper order, you come up with the man's name, Roy G. Biv. If you think of Roy G. Biv, every time you think of the colors in the visible spectrum, you will always know that red light has the longest wavelength and violet light has the smallest. And you will also know the order of all colors between them. Now that we know what the wavelength of light means, what does the amplitude of light mean? Simply put, the amplitude of a light wave tells how bright the light wave is. A dim light bulb produces light waves with a small amplitude, while a bright light bulb produces light with a large amplitude. If we had two light bulbs of the same color, but one was dimmer than the other, we could say that the light bulbs were both producing light of the same wavelength, but of different amplitudes. Similarly, if we had two light bulbs of different color, but the same brightness, we could say that the light bulbs produce light waves of equal amplitude, but of different wavelengths. There's a bit more to describing a light wave than just its amplitude and wavelength. The speed of the light wave is also important. After all, we know that light travels from place to place. If we turn on a light bulb, the light rushes from the light bulb and fills up the room. Therefore, light does travel. But how fast does it travel? Have you ever watched a thunderstorm and seen a lightning flash, but heard the thunder crash a few moments later? This happens because the light generated by the lightning flash travels more quickly than the sound it makes. The light reaches your eyes before the sound reaches your ears. For every 5 seconds between the time you see the lightning flash and the time you hear the thunder clap, the lightning is striking 1 mile away from you. Light then travels fast, much faster than sound. In fact, light travels in air with a speed of 3.0 times 10 to the 8th meters per second. In units you are more familiar with, that translate to 9.8 times 10 to the 8 feet per second, and that's really moving. To put it another way, light travels 190,000 miles every second. One thing that's very interesting about this number is that it does not change with the wavelength or amplitude of the light wave. Regardless of the color or the brightness of light, its speed in air is always 3.0 times 10 to the 8th meters per second. Since this value doesn't change, we call it a physical constant, and that is defined as a measurable quantity in nature that does not change. You will be introduced to several physical constants in this course, and the speed of light is the first one. Each physical constant has its own symbol. The symbol for the speed of light is c. When we say that c equals 3.0 times 10 to the 8th meters per second, we are giving you the speed of light. You do not need to memorize this number. We will always provide you with any physical constants you need to solve the assigned problems. Now that we know about the speed of light, we can finally speak of another very important means of describing a wave: frequency. Frequency is the number of wave crests or troughs that pass a given point each second. To best understand frequency, suppose you are standing in the ocean. If you look out at the waves, the distance between each crest is the wavelength. On the other hand, if you stand still and count the number of wave crests that hit you over a certain interval of time, that's the frequency. Think for a moment about the unit associated with frequency. Suppose you stand still in the water at the beach and count that 2 ocean wave crests hit you every second. You would report your measurement as 2 wave crests per second. However, since everyone at the beach can see that you are counting waves, you might just say 2 per second. What does per second mean? The unit meters per second is mathematically expressed as meters per second. Per second just means 1 per second. This means that the standard unit for frequency is simply 1 per second, and this unit is usually called the Hertz, abbreviated Hz, in honor of Heinrich Rudolf Hertz, a German physicist who greatly expanded our knowledge of light and its relationship to electricity. The frequency, wavelength, and speed of light are all related to each other by a simple equation: F, frequency, equals speed of light over wavelength. In this equation, F stands for frequency, C is for the speed of light, and lambda stands for wavelength. Notice how the units work out. Speed is in meters per second, while wavelength is in meters. When we divide the speed by the wavelength, meters cancel, and we are left with 1 per second, which is also called Hertz. This is a very important equation, and you should memorize it. Okay, now take some time and in your notebook on Module 3, work on practice problem number 4 and extra practice problems numbers 2, 3, and 4.